Welcome to What is a Logarithmic Scale? This video is part of a series in Foundations of Engineering by Conceptual Calculus. This cartoon from xkcd.com shows a graph of the fuel energy density of different fuels. On the left are sugar, coal, fat, and gasoline. Fat has more than twice the energy density of sugar, but that's not what you notice. The far right column shows that uranium is literally off the chart. Could we just adjust the scale and make this fit? Uranium is the tallest column, so it can take most of the page. Label the top of the y-axis as 80 million. Halfway to 80 million is 40 million, halfway up to that is 20 million, and halfway up to that is 10 million. Fill in the rest of the scale, and now uranium's 76 million fits on the graph. We didn't even need a whole box of paper. If the lowest line on the grid is 10 million, where are 19, 24, 39, and 46? They are so much smaller than 10 million that they are much less than 1 pixel tall. We can't see them. At least the cartoon managed to show them in a way that lets us see that 46 is bigger than 19. Surely that huge pile of paper can't be the best way to do it, though. The caption says, "Science tip: log scales are for quitters who can't find enough paper to make their point properly." That's a joke, of course. Log scales provide an alternative to this huge pile of paper. We use log scales to graph values that are different orders of magnitude. The order of magnitude tells us about how big the value is. Numbers from 1 to 9 are ones. The order of magnitude is 10 to the power 0. Numbers from 10 to 99 are tens. The order of magnitude is 10 to the power 1. From 100 to 999 are hundreds, 10 to the power 2. From 1,000 to 9,999 are thousands, 10 to the power 3. The power of 10 gives us a rough idea of the size, or magnitude, of the number. Let's look at how these different orders of magnitude show up on a familiar linear scale. I want to graph numbers from the ones to the thousands, so I make the top end of my scale 10,000. Then I fill in the numbers in between. On a linear scale, adding the same number takes you the same distance along the axis. For example, this green arrow represents adding 2,000. We start at 1,000, add 2,000, and end up at 3,000. We can also start at 6,000, add 2,000, and get to 8,000. Adding 2,000 always takes us the same distance. How do our orders of magnitude fit on this graph? Everything between 1,000 and 10,000 is in the thousands. That's most of the graph. The ones, tens, and hundreds are all squished together on the left end, in this little space between 0 and 1,000. On this scale, we can't tell the ones and the tens apart. Now, look at a logarithmic scale. I still want to go up to 10,000, but I break the space up differently. On a logarithmic scale, when we multiply by the same number, we go the same distance. For example, the green arrow represents multiplying by 10. Starting at 1, we can multiply by 10 and get to 10. If we start at 100, then multiplying by 10 will take us to 1,000. Multiplying by 10 always takes us the same distance along the axis. The ones, tens, hundreds, and thousands each get the same amount of space on the graph. We can fill in a few more numbers on our scale and see that multiplying by 10 still moves the same distance across. 400 times 10 takes us to 4,000, and it is still the same distance. That works with other numbers, not just 10. For example, we get from 2 to 10 by multiplying by 5. We also get from 40 to 200 by multiplying by 5, and it is the same distance along the axis. So, how does that relate to logarithms? For this video, I will use the natural log function, which has a base of e. It is possible to do the same thing with logs of other bases, so long as you stick with the same base throughout the entire problem. On this graph of the natural log function, we find the point where x is 1/2 and mark the y value of that point on the graph. Now we multiply the x value by 2 to get 1 and find the y value to go with that. Multiply the x value by 2 again to get 2 and find that y value. Multiply the x value by 2 again to get 4 and find that y value. Multiply by 2 again to get 8 and then again to get 16. Each time, we multiplied the previous value of x by 2 to get to the next point. That put the y values all the same distance apart. Multiplying the x by the same number moves the y by the same distance along its axis. Log scales make use of this property. Consider the function y equals 2 to the power x. It fits nicely on this linear scale because the numbers have the same order of magnitude. Now, zoom out on that graph. To include x equals 10 on the graph, we need room for a y value in the thousands. On that scale, the numbers from the previous version of the graph are all compressed into the x-axis. We can't see a difference between 1 and 4. They are both too small to show up at this scale. Next, instead of the actual y values, we graph their natural logs. This scale lets us see clearly the difference between 1 and 4 and still get 1024 on the same graph. To plot these points by hand, we could use a calculator to find the natural logs of all the y values. There is an easier way, though. We can change the scale on the vertical axis so that the graph paper does that work for us. Let's start putting in some grid lines where the y value is the natural log of a power of 10. Here's the natural log of 0.1, which is 10 to the negative 1, and then 1, which is 10 to the 0, and then 10, 100, and 1,000. Every time we multiply the y value by 10, the log of that y value moves up by the same distance. I want a few more grid lines. Here's the natural log of 3 and the natural log of 30. I'll put a few more of these in. Since I'm going to use these new grid lines, I can get rid of the original grid lines from the linear scale. I also want to simplify the labels a bit. We know we're working with natural logs, so all we really need to know is what number each line is the log of. Where I have y equals natural log of 10, which equals 2.3, I'm going to replace it with just 10. I'll do the same with 30 and with all the other grid lines. Next, I simplify the coordinates of the points. Where I have the natural log of 1024, I'll replace that with 1024. We know we're using the logs. I do the same with the other y values. Using these grid lines, we can graph the points without needing a calculator to find the natural logs of the numbers. To graph a point with a y value of 32, we put it just above the grid line labeled 30. Similarly, y equals 256 goes just below the 300 grid line. If we had a few more grid lines, we could plot our numbers very precisely. To see where the other grid lines go, it will help to zoom in on the graph. Remember that these lines all represent the natural logs of the numbers, so we use the natural log of 2 to put in the grid line labeled 2. It is not centered between 1 and 3. Because of the shape of the logarithm function, these grid lines get closer together as they go up. Here are 4, 5, 6, 7, 8, and 9. That fills in 1 decade, also called 1 cycle. A decade is the space on the graph occupied by a single order of magnitude. This is the ones decade. Above it is the tens decade, and below it is the tenths decade. Now we have graph paper that looks like this. We show how to plot points and graph functions on log scale graph paper in our next video, using logarithmic scale graph paper. Conceptual Calculus thanks VIVA, Virginia's Academic Library Consortium, and New River Community College for their generous support.